Now, among the test data in Figure 23 showing the effect of deadband on valve performance, I would like to introduce the closing direction response of valve B. This data was obtained from an open-loop test where step inputs from 0.5% to 10% were applied sequentially to 3 types of control valves under normal process conditions. This row of the table is for the closing direction, and for a step size of -10%, response values of 0.23 and 0.46 are recorded. These values correspond to time series indicators of how long it takes for the valve assembly to respond to input signal changes with flow. Additionally, this row marks the beginning of the valve B section, pairing with the preceding opening direction values of 0.19 and 0.33. The smaller the step, the more the flow response is delayed, which quantitatively demonstrates the impact of deadband on process variability.
Next, I would like to introduce the opening direction response data for valve B. In this row, response values of 5.61 and 7.74 are recorded. Compared to the 0.23 and 0.46 in the closing direction, the values have increased significantly, meaning valve B does not respond faithfully to each step until the input signal changes by approximately 5%. In the small step range, the valve stem may move, but almost no actual flow change occurs due to the deadband. Such large response times indicate that the dynamic characteristics in the opening direction are delayed and asymmetric, providing quantitative data that valve B has a lower ability to reduce process variability.
Next, I would like to introduce the response data for valve B in the closing direction for a step size of -2%. Here, the response values appear as 0.46 and 1.67. Compared to the 5.61 and 7.74 in the opening direction, the closing direction response is much faster for the same valve, showing highly asymmetric behavior depending on the direction. This phenomenon, where the dead time in one stroke direction is several times longer than the other, primarily stems from asymmetry in the positioner design. Such directional response mismatch makes it difficult to tune the loop optimally. Additionally, we can confirm that response delays occur even at a small step of -2% due to the deadband.
Following this, I would like to introduce the opening direction response values of 1.14 and 2.31 for valve B. Comparing these to the closing direction values of the same valve, the asymmetric behavior between opening and closing is confirmed again. Even for small steps, the response time exceeds 1 second. Generally, it is desirable to keep dead time within 1/3 of the total valve response time. Especially in fast loops where the process time constant is close to the dead time, it is critical to keep dead time as small as possible and consistent across both stroke directions. For reference, the response time indicator T63 discussed here refers to the time from the start of the input signal change until the output reaches 63% of that change. Next, I would like to introduce the response value of 1.04 for valve B in the closing direction for a step size of -5%. Valve B only begins to respond faithfully to each step once the input signal change reaches approximately 5%. This response time consists of the static time, which is the dead time, and the dynamic time taken to reach the 63% point once it starts moving. The primary causes of deadband are friction between the valve body and actuator, backlash in connections, and shaft windup in rotary valves. To reduce process variability, the goal is to lower the deadband of the entire valve assembly to 1% or less, and ideally to the 0.25% level.
Finally, I would like to introduce the opening direction response values of 0.59 and 1.14 for valve B. This is the final opening direction data for the valve B section. In actual regulatory control, valves are typically required to respond to small position changes of about 0.25% to 2%, and a high-quality valve should respond quickly to such small signals. Extensive testing has shown that spring diaphragm actuators consistently perform better than piston actuators for these small signal changes. Piston actuators tend to have poorer responsiveness to small signals due to higher friction. Given that most regulatory control signals are small steps, responsiveness to small signals is the key to reducing process variability. I'd like to introduce the row for the large step response of valve C in the valve response time summary table. This row represents a case where the valve is moving in the closing direction, and the input step size is minus 10%. In this case, the dead time, TD, is measured at 0.41 seconds, and the total response time, T63, is 1.14 seconds. Here, TD is the static delay from when the input changes until the output actually begins to move, and T63 is the time from the start of the input change until the output reaches 63% of that change. For a large step like minus 10%, valve C shows a relatively quick response, but the difference becomes clear when compared to the small steps we'll see later.
Now let's look at the response time of valve C in the opening direction. Under these conditions, the dead time TD is 4.4 seconds, and the total response time T63 is 5.49 seconds. Comparing this to the closing direction we just saw, where TD was 0.41 seconds and T63 was 1.14 seconds, we can see that for the same valve, the dead time is nearly 10 times longer in the opening direction. This asymmetric behavior, where the dead time differs by 3 to 5 times depending on the direction of travel, mainly stems from the asymmetric characteristics of the positioner design. Such asymmetry makes it difficult to optimally tune the loop and becomes a factor that limits overall performance.
I'll now introduce the row showing how valve C reacts to a small step input. When a small step of minus 2% is applied in the closing direction, both TD and T63 are recorded as NR. Here, NR stands for no response. In other words, valve C does not respond with any change in flow to a small signal change of minus 2%. This is because an excessive deadband in the valve simply absorbed the small input signal. In regulatory control, most signal changes are small, often less than 1%. A valve that cannot respond to such small signals is effectively useless in reducing process variability.
Next, I'll introduce the response time of valve C in the opening direction, which pairs with the no-response condition in the closing direction we just saw. In this case, the dead time TD is measured at 5.58 seconds, and the total response time T63 is 7.06 seconds. Even though it's in the same small step range, while it was completely unresponsive in the closing direction, it does respond in the opening direction, though the time is very long. This once again demonstrates that the opening and closing behaviors of valve C are highly asymmetric. Valves with such long response times and direction-dependent behavior seriously degrade control quality in fast process loops. Let's look at the response when the step size for valve C in the closing direction is increased to minus 5%. Under this condition, the dead time TD is 2.16 seconds, and the total response time T63 is 3.9 seconds. What's noteworthy is that the valve, which was NR or unresponsive at minus 2%, finally began to respond once the step was increased to minus 5%. This shows that a change in flow only occurs when the input signal is large enough to overcome the valve's deadband. However, even when it does respond, both the dead time and total response time are long, making this behavior unsuitable for precise process control.
In this section, I'll introduce the part of the Figure 2 for valve response time summary table containing the measured values for the opening operation. 2 time values are recorded for each step size. One is TD, the dead time, representing the static time, and the other is T63, the time from the start of the input signal change until the output reaches 63% of that change. The measured values for the opening operation here are 0.69 seconds and 1.63 seconds. The first value corresponds to the dead time and the second to T63. By looking at these two values together, we can quantitatively determine how quickly the valve assembly reacts to a signal.
Here, I'll introduce the last item for the closing operation in the valve response timetable, along with the definition of the concept of inherent flow characteristic. For the closing operation at a step of minus 10, the dead time is 0.53 seconds and T63 is 1.25 seconds. You'll also see the notation NR, which means no response. Moving on to the characteristic curves, the horizontal axis is percent travel and the vertical axis is percent flow, or CV. Since valve flow is determined by both travel and the differential pressure across the valve, inherent valve characteristic tests are traditionally performed under constant pressure drop conditions. While this differs from actual operating conditions, it allows for a systematic comparison between different valve characteristic designs. Under the specific condition of constant pressure drop, flow becomes a function only of the valve travel and the inherent design of the valve trim. The characteristics obtained this way are called the inherent flow characteristic of the valve.
In this section, I'll introduce the three types of inherent flow characteristics and the concept of valve gain. The inherent characteristics obtained under constant pressure drop are named linear, equal percentage, and quick opening. Full descriptions of each can be found in the conventional characterized valve plugs section of Chapter 3. Valve gain is defined as the ratio of the incremental change in flow output to the corresponding increment of valve travel input that caused the flow change. In other words, the inherent valve gain is the slope of the inherent characteristic curve. A linear characteristic has a constant inherent valve gain throughout its range, and a quick opening characteristic has an inherent gain that is greatest at the lower end of the travel range. Conversely, an equal percentage valve has the greatest inherent valve gain when the valve travel is at its maximum.
Now, I'll discuss the possibility of changing inherent characteristics and the transition to the more important installed flow characteristic. Because the inherent valve characteristic is an inherent function of the valve flow passage geometry, it does not change as long as the differential pressure is held constant. Many designs, such as rotary ball valves, butterfly valves, and eccentric plug valves, have inherent characteristics that cannot be easily changed. However, most globe valves allow for the replacement of valve cages or plugs to modify the inherent flow characteristic. While knowing the inherent valve characteristic is useful, what is more important for process optimization is the installed flow characteristic of the entire process, including the valve and all other equipment in the loop. This installed flow characteristic and gain are shown in Figure 2.5.
This shows the changes in flow characteristic and gain when the valve is actually installed in the piping. In this chunk, I'd like to introduce the definitions of installed flow characteristic and installed gain. The installed flow characteristic is defined as the relationship between the flow through the valve and the valve assembly input when the valve is installed in a specific system and the differential pressure across the valve is allowed to change naturally, rather than being held constant. An example of such an installed flow characteristic is shown in the upper curve of Figure 2.5. In this figure, flow is plotted against valve travel, which is more familiar to us, rather than valve assembly input. The installed gain, shown in the lower curve of Figure 2.5, is a plot of the slope of the upper curve at each point. These types of installed flow characteristic curves can be obtained under laboratory conditions by operating the entire loop at some nominal set point with no load disturbances.
Here, I'll introduce the actual measurement procedure for the installed flow characteristic and installed process gain. First, the loop is placed in manual operation. Then, the flow is measured and recorded as the input to the control valve assembly is manually driven through its full travel range. A plot of these results is the installed flow characteristic curve shown in the upper part of Figure 2.5. Next, by evaluating the slope of this flow curve at each point and plotting it, we get the installed gain curve in the lower part of Figure 2.5. Meanwhile, the installed process gain at a single operating point can also be measured in the field using open-loop step tests, as shown in Figure 2.3. At any operating condition, the installed process gain is simply calculated as the ratio of the percent change in output, flow, to the percent change in valve assembly input signal.
Now, let's discuss the purpose of characterizing inherent valve gain. The reason for characterizing inherent valve gain through various valve trim designs is to provide compensation for other gain changes occurring within the control loop. Our ultimate goal is to keep the loop gain reasonably uniform over the entire operating range, which allows us to maintain a relatively linear installed flow characteristic for the process. The definition of this installed flow characteristic is covered in Chapter 1. Also, please keep in mind that due to the definition of the measurement method, the installed flow characteristic and installed gain represented in Figure 2.5 are not values for a single valve, but are actually the installed gain and flow characteristic for the entire process.
Next, let's look at the relationship between changes in process gain and valve selection. Generally, the gain of the unit being controlled changes with flow. For example, the gain of a pressure vessel tends to decrease as throughput increases. In a situation where the process gain decreases with flow, a process control engineer would want to use a valve whose gain increases with flow. This is where an equal percentage valve is appropriate, Since the gain of an equal percentage valve increases as flow increases, it can offset the decreasing gain on the process side, helping to keep the overall loop gain more uniform.
Now, I'll explain how the characterization of inherent valve gain relates to the gain compensation of the entire loop. The reason for intentionally shaping the inherent gain through valve trim design is to offset other gain changes occurring within the control loop. The final goal is to keep the loop gain relatively uniform across the entire operating range to make the installed flow characteristic of the process close to linear. Theoretically, a loop is tuned for optimum performance at some set point flow condition. To preserve this optimum performance, the loop gain must be kept as constant as possible, even as flow varies around that set point. If the change in loop gain due to the inherent valve characteristic does not exactly compensate for the changing gain of the unit being controlled, the loop gain will fluctuate as the installed process gain varies. This not only makes process optimization more difficult, but also creates a risk where the loop gain changes enough to cause instability, limit cycling, or other dynamic issues.
If the two inverse relationships explained earlier are ideally balanced, the installed flow characteristic of the entire process becomes closer to linear. In practice, the variation in loop gain should not exceed a 4-to-1 ratio. If this ratio is exceeded, the dynamic performance of the loop suffers unacceptably. However, there is nothing magic about this 4-to-1 figure. It is simply a value that many control practitioners agree produces an acceptable range of gain margins in most process control loops. This guideline forms the basis for the following NTEC gain limit specification. The source is the Control Valve Dynamic Specification, version 3.0, November 1998, from NTEC Control Incorporated, Toronto, Ontario, Canada. Here, the loop process gain is defined as 1.0, which is the transmitter span percentage divided by the controller output percentage, and the nominal range is 0.5 to 2.0, representing a 4-to-1 ratio. It should be noted that this definition of the loop process includes all devices in the loop configuration except for the controller. I would like to introduce what constitutes the process gain. The process gain is the product of the gains of various devices, such as the control valve assembly, the controlled system like a heat exchanger or pressure vessel, the pump, and the transmitter. Since the valve is also part of the loop process as defined here, it is important to select a valve style and size that produces an installed flow characteristic sufficiently linear to stay within the specified gain limits over the entire operating range. If too much gain variation occurs in the control valve itself, it leaves less flexibility in adjusting the controller. Therefore, it is good practice to keep as much of the loop gain in the controller as possible. Additionally, while the 4-to-1 gain change ratio in the loop is widely accepted, not everyone agrees on the specific limit values of 0.5 to 2.0.
I'll now discuss the differing opinions regarding the gain limit values. Some industry experts argue for using loop process gain limits from 0.2 to 0.8. This also maintains a 4-to-1 ratio. However, the potential danger inherent in using this reduced gain range is that at the low end of the gain range, the valve could swing significantly even during normal operation. Good operating practice is to keep valve swings below approximately 5%. Conversely, there is also a danger in letting the gain become too large. If the loop gain becomes too high at some point in the travel, the loop can become oscillatory or even unstable.
Now, I would like to introduce the concept of the control range. To ensure good dynamic performance and loop stability over a wide range of operating conditions, industry experts recommend that loop equipment be engineered so the process gain remains within the range of 0.5 to 2.0. For process optimization, a valve style and size must be chosen that keeps the process gain within the selected gain limit range over the widest possible set of operating conditions. Because minimizing process variability is so dependent on maintaining a uniform installed gain, the range over which a valve can operate within the acceptable gain specification limits is called the control range of the valve. This control range varies dramatically with the valve style. Figure 2.6 compares a line-size butterfly valve to a line-size globe valve.
We will compare the effect of the choice of valve style on the overall control range.
I'll now discuss the impact of the control valve style on the control range. Comparing the same line size, the globe valve has a much wider control range than the butterfly valve. V-notch ball valves or eccentric plug valves generally fall somewhere between these two. On the other hand, because butterfly valves typically have the narrowest control range, they are best suited for fixed-load applications. Even then, sizing must be done carefully to achieve optimal performance. If the inherent characteristic of a valve could be selected to exactly compensate for the system gain change with flow, the lower curve representing the installed process gain would be essentially a straight line at a value of 1.0. However, since it is impossible to provide an infinite variety of inherent valve trim characteristics, such a precise gain match is realistically almost impossible.
The situation where precise gain matching is difficult can be partially compensated for. However, the problem is that some styles, such as butterfly or ball valves, do not have valve trim alternatives that allow the inherent characteristic to be easily changed. In these cases, this can be alleviated by incorporating a nonlinear cam into the feedback mechanism of the positioner to change the inherent characteristic of the valve assembly. The nonlinear feedback cam modifies the relationship between the valve input signal and the valve stem position, allowing the desired inherent characteristic to be achieved for the entire valve assembly without relying solely on changing the valve trim design. Using positioner cams to change valve characteristics is sometimes useful because it allows for adjustment without modifying the trim design. However, in most cases, the effect is limited. This is because the cam also dramatically changes the positioner loop gain, which severely restricts the dynamic response of the positioner. Therefore, characterizing the valve with cams is generally not as effective as characterizing the valve trim itself. That said, for rotary valves where the only other option is often no characterization at all, using cams is always the better choice. Meanwhile, some electronic devices attempt valve characterization by electronically shaping the I/P positioner input signal ahead of the positioner loop.
Next, we turn to sizing and selection.
This electronic technique takes a linear 4 to 20 milliamperes controller signal and recalibrates the valve input signal using a pre-programmed table of values. In doing so, it produces the valve input required to achieve the desired valve characteristic. This method is referred to as forward path or set point characterization. Since this characterization occurs outside the positioner feedback loop, it has an advantage over characterized positioner cams. It avoids the problem of changes in the positioner loop gain. However, this method also has dynamic limitations. For example, in certain parts of the valve range, specifically the flat regions of the characterizing curve, a 1% process signal change might be narrowed through this characterization process to only a 0.1% signal change to the valve.
Due to the flat region problem mentioned earlier, many control valves are unable to respond to signal changes this small. Therefore, the best process performance is achieved when the required flow characteristic is obtained by changing the valve trim itself, rather than using cams or other methods. Properly selecting a control valve designed to produce a reasonably linear installed flow characteristic over the system's operating range is a critical step in ensuring optimum process performance. Next, I will introduce valve sizing. In an attempt to optimize performance by reducing process variability, valves are sometimes oversized. This results from using line-size valves, especially high-capacity rotary valves, or from conservatively adding multiple safety factors at various stages of the process design. Such oversizing worsens process variability in two ways.
First, an oversized valve puts too much gain in the valve, reducing the flexibility available for adjusting the controller. Best performance is achieved when most of the loop gain comes from the controller. Looking at the gain curve in Figure 2.5, the process gain becomes quite high in the region below approximately 25% valve travel. If the valve is oversized, it is more likely to operate in or near this region, and this high gain often means the controller gain must be reduced to avoid loop instability. Of course, reducing the controller gain comes at the cost of increased process variability. The second way is that an oversized valve is likely to operate more frequently at lower valve openings, where seal friction can be greater, particularly in rotary valves.
Now, I would like to discuss the impact of oversized valves on process variability. When a valve is oversized, a disproportionately large flow change occurs for the same amount of valve travel. In other words, the flow fluctuates significantly even with a very small movement. Because of this, process variability associated with dead band due to friction is greatly exaggerated. Since a small change in travel leads directly to a large change in flow, precise control becomes difficult. Furthermore, it is important to note that regardless of its actual inherent characteristic, a severely oversized valve tends to act like a quick opening valve.
I'd like to introduce how an oversized valve behaves. If a valve is severely oversized, it will behave like a quick opening valve regardless of its original inherent characteristic. As a result, the installed process gain becomes abnormally high in the lower lift regions. You can see this in Figure 2.5. Also, when oversized, the valve reaches system capacity at a relatively low travel, causing the flow curve to flatten out in the higher travel range. Once the travel exceeds 50 degrees, the process gain approaches zero, making the valve completely ineffective for control purposes. Since the flow barely changes even with large changes in travel, there is little hope of achieving acceptable process variability in this region. The valve shown in Figure 2.5 is a case of total misapplication in this scenario, as its control range is limited to approximately 25 degrees to 45 degrees.
I'll now explain how the misapplication we just saw occurs. The situation shown in Figure 2.5 happened because a line-sized butterfly valve was chosen primarily due to its low cost. The loss of profit resulting from sacrificing process variability due to poor dynamic performance of the control valve was not considered at all. Unfortunately, this situation is often repeated. Process control studies show that in some industries, the majority of valves currently in control loops are oversized for the application. While it might seem counterintuitive, it often makes more economic sense to select a control valve for present conditions and then replace the valve when conditions change. When selecting a valve, it is important to consider the valve style, inherent characteristic, and valve size that will provide the broadest possible control range for the application.
Next, we turn to economic impact.
Now, let's discuss the economic results. Carefully considering factors such as deadband, response time, and installed gain, especially under actual process load conditions, can have a dramatic impact on the economic results of an operating plant. More and more control valve users are focusing on these dynamic performance parameters as a means to improve process loop performance. While many of these dynamic performance parameters can be measured in an open-loop situation, their impact becomes clear when closed-loop performance is measured. The closed-loop test results shown in Figure 2.7 demonstrate the ability of 3 different valves to reduce process variability over different tuning conditions. This diagram plots process variability as a percentage of the set point variable on the vertical axis and the closed-loop time constant, which is a measure of loop tuning, on the horizontal axis.
This represents the valve control performance and response characteristics in a closed-loop configuration.
I'll explain how to read the curves in Figure 2.7. The horizontal line labeled manual shows how much variability is inherent in the loop when no attempt is made to control it, meaning in an open-loop state. The line sloping downward to the left, marked minimum variability, represents the calculated dynamic performance of an ideal valve assembly with no nonlinearities. All real valve assemblies will normally fall somewhere between these two conditions. Even if all valves theoretically meet static performance purchase specifications and are considered equivalent, their actual dynamic performance differs. In the figure, valve A follows the trend of the minimum variability line well over a wide range of controller tunings. This valve demonstrates excellent dynamic performance with minimum variability.
Now, let's look at how the performance gap between valves widens when tuning is done aggressively. In contrast to valve A, the designs of valve B and valve C perform poorly. As the system is tuned more aggressively, that is, in the direction of decreasing closed-loop time constants, the variability of these two valves actually increases. While all 3 valve designs are capable of controlling the process and reducing variability, 2 of them do it less effectively. Let's consider what would happen if the poorer performing valve B was replaced with the best performing valve A, and the system was tuned to the same closed-loop conditions. We will cover the quantitative effects in the following section.
Now, I'd like to introduce the economic effects of replacing a valve, as confirmed by closed-loop testing. Figure 2.7 shows the closed-loop performance curve, where process variability, expressed as a percentage of the set point variable, is plotted against the closed-loop time constant on the horizontal axis. The closed-loop time constant is an indicator of the degree of loop tuning. Let's consider a case where a lower-performing valve B is replaced with the highest-performing valve A, and the system is tuned to a closed-loop time constant of 2.0 seconds. According to the test data, this replacement alone improves process variability by 1.4%. While this number may seem small, the effect is significant when accumulated every minute of every day. By maintaining closer adherence to the set point, it is possible to move the set point closer to the lower specification limit, thereby reducing raw material consumption. In this example, a 1.4% improvement translates to a raw material saving of 12,096 US gallons per day. Assuming a material cost of $0.25 per gallon, the highest performance valve contributes $3,024 per day directly to profits, which amounts to an impressive $1,103,760 per year.
This example provides strong evidence that a superior control valve assembly can have a profound economic impact. However, increasing profits through tighter control is not limited to just one method. There are various paths that precise control can take, such as decreased energy costs, increased throughput, and reduced reprocessing costs for out-of-spec products. While the initial cost might be higher for the best control valve, the few extra dollars spent on a well-engineered control valve can dramatically increase the return on investment. In fact, it is common for that extra initial cost to be paid for in a matter of days. As a result of studies such as these, the process industries have become increasingly aware that control valve assemblies play an important role in loop, unit, and overall plant performance.
The process industries have also realized that traditional methods of specifying a valve assembly are no longer adequate to ensure the benefits of process optimization. Static performance indicators such as flow capacity, leakage, materials compatibility, and bench performance data are certainly important. However, these static indicators alone are not sufficient to deal with the dynamic characteristics of process control loops. In other words, looking at specifications in a static state cannot properly define how the loop behaves during actual operation.
To summarize, the control valve assembly plays an extremely important role in producing the best possible performance from the control loop. Process optimization means optimizing the entire process, not just the control algorithms used in the control room equipment. The valve is called the final control element because the control valve assembly is where process control is actually implemented. It makes no sense to install an elaborate process control strategy and hardware instrumentation system capable of achieving 0.5% or better process control, and then implement that strategy with a 5% or worse control valve. Audits performed on thousands of process control loops have provided strong proof that the final control element plays a significant role in achieving true process optimization.
Profitability increases when a control valve has been properly engineered for its application. Control valves are sophisticated, high-tech products and should not be treated as a commodity. Although traditional valve specifications play an important role, specifications must also address real dynamic performance characteristics if true process optimization is to be achieved. It is imperative that these specifications include parameters such as dead band, dead time, and response time. Finally, process optimization begins and ends with the optimization of the entire loop. Parts of the loop cannot be treated individually to achieve coordinated loop performance. Likewise, the performance of any part of the loop cannot be evaluated in isolation. Finally, I would like to discuss the conditions under which valve performance tests should be performed. Isolated tests conducted under non-loaded, bench-type conditions are not sufficient. This is because such tests can never provide the performance information that is obtained from testing the hardware under actual process conditions. To properly understand the true performance of a valve, the hardware must be tested under actual operating conditions, that is, in a real environment under load. Please remember that the prerequisite for securing reliable performance data is testing under actual field process conditions, not on a workbench.